Hello students, welcome back. This video is more or less a continuation of the second video, not the third. In the second video, we established the derivative at x equals to a, and then we went on to define the derivative function. We're going to continue from here. Now we're going to study some formulas to calculate the derivative function when the original function is sufficiently simple. Consequently, we're going to learn a lot better method than using the definition of the derivative to calculate the derivative, kind of like these problems you see. Newton quotient computation and the limit, or average rate of change and the limit, those kind of things. Even worse, this kind of computation. Yes, it was possible, but not efficient at all. We're going to do it in a completely different fashion now, and this is where we start. Some derivative rules for really simple cases. So simple that I usually call them trivial rules. First, the derivative of a constant function is always 0. Second, the derivative of sum is sum of the derivatives. And finally, the coefficient. You can multiply a coefficient a either before or after. No difference. Now this coefficient must be really coefficient. If this also has an x expression in there, it doesn't work. If you want to see the proof, well, there they are. But most students probably will not be interested, so we'll just use them. Next, the power rule. The derivative of the power function goes kind of like this. Power comes out as a coefficient and subtract 1 from the power. As for the proofs, well, only for the interested students. I'm not going to come back and talk about any of these, at least for now. In the appendix I will, but not for now. Okay, let's go to an example problem. Oh, let's keep this power rule here. Here's a good example. Let's find out a derivative function of this given function. Alright, let's align the equality. Okay, let's find out the derivative of x cubed. Just put it in there, and what happens? Multiply by 3 and then subtract 1 from the power. Good. Next, again the same rule with the coefficient. Multiply by 2, so 6x, and then subtract 1 from the power. First power. First power, you don't have to write it, right? So let's remove it. Next, 4x, well, the first power was there before, so apply the same rule. Multiply by 1, so we have 4, and subtracting 1 from the power, we get 0 power. What is 0 power? That's just 1, isn't it? So times 1 doesn't change anything. And again, I don't need this. And that's the end of the story, right? Because the derivative of this constant is 0. So either you have plus 0 or without it, we're going to get the same answer there. Let's open up this cell. Yes, that's correct. We don't need duplicate answers, so let's remove this. And that's how the power rule works, along with the trivial rules, especially this one and that one. One more exercise, all right? Oops. This time, we have a bunch of radical expressions, but we don't have any rules related radicals here. All I see is a power rule, so it's going to be better if you re-express all this into a power form. And let's go ahead and do that. What is square root of x in the power form? It's x to the what power? 1/2 power. That was easy. Now how about this fraction? Number part is 4 and x to the negative 1/2 power. Why negative? Because this is in denominator. Why 1/2? Because we have square root. If this had been cubic root, it would be 1/3. How about this part? X to the first power times x to the 1/2 power. And the same base, we have to add up the power, so total will be x to the 3/2 power. And that is the original function. Now the derivative function. What do? We just use this rule over and over again. 3 is coefficient, there will be 4, alright. And then let's multiply the power. And then subtract 1 from the power. Okay, next. 4 is coefficient, so stay there. And multiply by the power, negative 1/2. And subtract 1 from the power. Negative 1/2 minus 1, negative 3/2. Finally, the last term. 2 is coefficient, multiply by the power, and subtract 1 from the power. And there goes the solution. Personally, I'd rather stop here. I don't see any reason for any kind of simplification, but if you do decide to simplify, okay, you can go ahead and do that. This is 3/2 x to the negative 1/2 power, and then minus 2x to the negative 3/2 power, and then minus 3x to the 1/2 power. I guess that's a simplification. Let's check. Let's open up this cell and compare. Yes, that's correct. There's no need to have duplicate answer keys, so let me remove these. So that's how the power rule works. Oh, by the way, if you use the formula method, you can do this kind of problem a lot easier. For example, this kind of problem, we used what? Newton quotient method for this kind of limit computation, or average rate of change formula, kind of like this. We don't need any of those. You can just apply the formula. Derivative of 3x squared, that's 6x. Derivative of x, that's just 1. And then minus 2, that's constant, so that goes away. So this is a derivative function. Plugging in x equals a negative 1, do a bit of a computation, you get the answer. This is how you do these kind of problems. Nobody does it this way. We did it simply because we just learned the definition of the derivative, but afterward we never do it like that. Let's see, do we have a little bit more time for exponential and logarithm? Okay, let's go ahead and do that. 2 more rules. Derivative of natural exponential function, stay the same. Derivative of natural logarithmic function, 1 over x. For arbitrary base, we have a little bit more complicated rules, but we're going to deal with those later, and a couple of weeks later in chain rule. Okay, here we go. Oh, I love this problem. We have bunch of x and e's, rather confusing. But the key is to recognize that only one of them is exponential function and the others are power functions. That's exponential, so stay the same. And next one is the power function. So power comes out as coefficient, and subtract 1 from the power. Next, this one is equivalent to first power, isn't it? So multiply by 1 and subtract 1 from the power. We have 0 power, that's just 1, so multiplying by 1 doesn't change anything, so this is just fine. How about the next one? This is equivalent to actually 1 over e times x. So let's apply the derivative rule. 1 over e, and then multiply by 1 and subtract 1 from the power so that we have 0 power. That goes away. So that's the derivative. Next, e over x is equivalent to x to the negative first power like this. I think that's the only term that is worthy of some color coding. Okay, let's apply the power rule here. Multiply by negative 1, so negative, and x to the subtract 1 from the power, negative second power. Let's emphasize in red. Now how about the final term here? E to the e power, is that an exponential or is that power? Actually, it's neither. It's a constant because there's no x in there. So the derivative of this is just 0, and you can write minus 0 or plus 0, it doesn't really matter. You can throw it away if you like. Well, in this problem I'd like to keep it because there are so many expressions, they are kind of fusing. So I'd like to keep the same order so that everybody can see the first term came from the first term, second term came from the second term, and so on and so forth. In this kind of problem, it is very important not changing the order. You see, the work part of the problem is not just a process to get the answer, but it's justification. And if you just mingle around, then you fail to justify the problem. Consequently, you may get full credit for the answer part, 30%, but the other 70%, well, you may lose some hefty credit from there. So with correct answer, you end up with 5 out of 10, or even worse. Yes, that can happen. How about the next problem? As a matter of fact, this is really easy. If you use the log rule, log of y plus 2 log of y plus 3 log of y, because in log function, power comes out as coefficient, so this whole thing is 6 log of y. Oops. Therefore, if I take the derivative, what do you get? 6 times the derivative of log is 1 over y, so this whole thing is 6 over y, and that's the end of the problem. We have the answer key here, so we don't need duplicate answer key, so let me remove it. The same thing goes here. You can always look up the answers from my notebook. Okay, how much time do we have? Do we have sufficient time to deal with these kind of problems? Probably not. So let's do these problems in a separate video.